Welcome to the Unit 12 guided practice for test remediation. Looking at the academic vocabulary, we need to memorize these for the test. Pressure is the force per area exerted by one object on another. Partial pressure is the pressure of a specific gas in a mixture of gases. Atmospheric pressure is the pressure that is exerted by the atmosphere. STP stands for standard temperature and pressure. Standard molar volume exists at STP and is 22 liters per mole. Our isochloric is the volume is held constant, stands for the volume being held constant. Isothermal, the temperature is being held constant. Isobaric is the pressure is held constant. An ideal gas is a perfect gas, a gas that behaves according to the kinetic molecular theory. KMT is the kinetic molecular theory and is the theory used to study ideal gas behavior. Boyle's law is an isothermal condition of a gas where the volume and pressure are inversely proportional. Charles's law is an isobaric condition of a gas where the volume and temperature are directly proportional. Gay-Lussac's law is an isochoric condition of a gas where the pressure and temperature are directly proportional. The combined gas law is the gas law that combines Boyle's, Charles, and Gay-Lussac's law, where volume, temperature, and pressure all change. And the ideal gas law is the equation that describes the volume, temperature, and pressure of a specific amount of gas. It says a reaction occurs at negative 325 degrees Fahrenheit and 6,000 pascals. It says convert these units convert the values to units compatible with the ideal gas equation. So ideal gas equation we're going to need in liters, atmospheres, moles, and Kelvin. And so the first conversion we can do is convert our negative 325 Fahrenheit into Kelvin. So first we have to take it and use the equation where we have C equals Fahrenheit minus 32 times 5/9. We plug that in, minus 32 times 5/9, and we get negative 198.33. And then we add to take it from Celsius, because this is now Celsius, to Kelvin. We just add 273 and we get 74.67 Kelvin. So now we have our temperature in Kelvin. All we have to do now is get the pascals into atmospheres. So it's 6,000 pascals, and there is 101,325 pascals in 1 atmosphere. And so we will get 0.0592 atmospheres of pressure. Looking at B, it says a reaction occurs at 50 degrees Celsius and 750 millimeters of mercury. Convert these units to compatible with the ideal gas equation. So the answers that we should get for this, we should get 323 Kelvin and we should get 0.987 atmospheres. Use the same techniques that we used above and see if you can't get those answers. C, what is STP? STP stands for standard temperature and pressure, which standard temperature is 0 degrees Celsius and standard pressure is 1 atmosphere. Looking at Dalton's law of partial pressure, it says what is the total pressure in a container that collects 140, or not 140, 1.4 atmospheres of nitrogen, 50,000 pascals of carbon dioxide over water at 50 degrees Celsius. So we have the water vapor chart here, and we see that at 50 degrees Celsius we will have a pressure of 92.5 torr. And what we can do is we just need to get all these units in the same, or all these pressures in the same unit, and then just add them together. And so we have 1.4 atmospheres. And so we'll go ahead and let's convert these to pascals. So 1.4 atmospheres, not pascals, but torrs, excuse me. 1 atmosphere is 760 torrs. And we're doing that because we see we have torr up there. And so we would get 1064 for our nitrogen. And then we would take this and we would convert our 50,000 pascals, and there is 101,325 pascals in 760 torrs. And so we get this, and we will get that we have an amount of 375 torrs. So what we would do is add partial pressure. We just add all the pressures together. That pressure plus that pressure plus that pressure. Now that they're all in the same unit. And we would get a total pressure of 1,531.5 torr. Next picture says next question, draw a picture illustrating why the vapor pressure increases as the temperature increases. So vapor pressure is going to increase as temperature increases, because what we'll have is we'll have water molecules at the very top of the water that create the vapor pressure, and as the bottom water molecules heat up, they start to vibrate more, and the bonds, the intermolecular bonds that are holding these waters molecules on top to the bottom, since the bottom ones are vibrating so much back and forth, that they very easily come off, and so therefore they create more pressure. What is Dalton's law of partial pressure, and when does it apply? Dalton's law of partial pressure applies generally when we use it when things are collected over water. Gases are hard to collect, and so therefore we collect them over water to give us an ability to kind of put them in a beaker where we just know it's that substance in water vapor. Dalton's law of partial pressure can apply anytime that you have multiple gases in a single container. Moving on to the combined gas law. Combined gas law is P1 V1 all over T1 equals P2 V2 all over T2. And it says calculate the final volume, and final volume of a sample of gas that is initially 250 milliliters at 20 degrees Celsius when the pressure is 1.2 atmosphere. As the reaction proceeds, the sample increases to 80 degrees Celsius and the pressure drops to 0.8 atmospheres. And so what we would do is we have our initial pressure of 1.2 atmospheres, our initial volume of 250 milliliters, and our initial temperature of 20 degrees Celsius, but we convert that to Kelvin, which would be our 293 Kelvin, equals our new pressure, or P2, of 0.8 atmospheres, our V2, which we're solving for, and then our T2, which is 353 Kelvin. Now what we will do is crisscross, so multiply those together, multiply those together. And then what we will do is we'll take it after we do that, and then we will divide this answer that we multiplied in purple by our 1.8 times 293. We'll divide that out and we should get a volume of 451.8 milliliters. Next problem, it says calculate the final, and that should say pressure when 400 milliliters of carbon dioxide is sealed at STP, then heated to 50 degrees Celsius at a constant volume. So if something is held constant, P1 V1 all over T1 equals P2 V2 all over T2. If something is held constant, you just erase it from the combined gas law. So since volume is constant, volume goes away, and we would use this equation. Now the answer that you should get is 1.18 atmospheres. Another hint to this one, remember that STP is standard temperature and pressure. So that means that the standard temperature, the initial temperature is going to be 0 degrees Celsius. The initial pressure would be 1 atmosphere. And remember, you're going to solve for pressure, P2. C, what is the combined gas law under isobaric conditions? So isobaric means that it is a constant pressure. And remember, all you do is just erase pressure, and we get V1 all over T1 equals V2 all over T2. Looking at the kinetic molecular theory, it says list all the tenets of the kinetic molecular theory. Number 1, a gas consists of small particles traveling in a straight line motion and obeying Newton's law of motion. 2, molecules of gas have 0 volume. 3, collisions between gas molecules have 0 energy transfer. 4, there are no attractive or repulsive forces between the molecules. And 5, the average kinetic energy of a molecule is defined by 3 over 2 kT. Those are the tenets of the kinetic molecular theory, the postulates that we have. It says give example where the above fail. So the gas particles, when they're moving, they don't always move in a straight line motion. Molecules of gas occupy some volume. Collisions between the gas molecules do have energy transfers, and there are attractive and repulsive forces when we're talking about the kinetic molecular theory. And so what we use the kinetic molecular theory for is to give us a basis to start understanding gases. Now, C is what is the difference between a real gas and an ideal gas. An ideal gas follows every postulate of the kinetic molecular theory. It's a perfect gas. A real gas is going to have, it's going to vary slightly from the kinetic molecular theory because there are collisions, there are energy transfers, they do have occupy a volume. And so those are ways that a real gas is what we really get. A, for the ideal gas law, it says a sample of 2.5 moles of nitrogen gas occupies 10 liters at 400 degrees Celsius. What is the pressure of the container? So the ideal gas law is PV equals nRT. Pressure volume, N is the number of moles, R is ideal gas law constant, and T is temperature. Remember that our pressure needs to be in atmospheres, volume needs to be in liters, and temperature needs to be in Kelvin, and N needs to be in moles. So it says what is the pressure? So we will be solving P equals nRT all over V. So we have 2.5 moles. We have R, which is 0.0821. We have a temperature of 400 degrees Celsius, which we add 273 to it, and we get 673 Kelvin all over a volume of 10 liters. We plug this in and we get 13.8 atmospheres of pressure. B, calculate the mass of carbon dioxide in a flask that occupies 250 milliliters. The flask has a pressure of 1.4 atmospheres and 450 Kelvin. So when we're solving for mass and it asks us to solve for mass, we're really solving for N. So what we will get is PV all over RT equals N. And we're solving for moles. Now it's carbon dioxide. So once I solve for moles, I can get the mass by multiplying it by the molar mass of carbon dioxide. So what we end up getting is we end up getting a pressure of 1.4 times a volume of 0.25 liters. We have to convert that, divided by 0.0821 and a temperature of 450 Kelvin. And what we get is we get a mole value, which is very small in this case, of 0.00947 atmospheres, sorry, not atmospheres, moles. And then we know that 1 mole of CO2 has a mass of 44 grams. And so we multiply it out and we will get a mass of 0.417 grams. C, when can you use the ideal gas equation? The main difference between the ideal gas equation and using the combined gas equation is the fact that in the combined gas law, you have a change in either pressure, volume, or temperature. This is just using it to calculate gases that aren't going through a change.